Hey everybody, let's continue our discussion on simple harmonic motion with the world's fastest recap of what we did last time. So let's say you have a mass connected to a spring and it's bouncing around on a smooth surface. Let's call this X. Okay, so in the X direction, let's say if I'll put the origin over here. So let's say the block is on this side. So now the spring is stretched. So then the spring force would be this way. Right, and then here's our free body diagram. So in the X direction, we got minus spring force. So K and then X, and then that's it. Mass times acceleration. And right, you see if I divide both sides by m, acceleration is the second derivative of position. Right, so this is simple harmonic motion. The acceleration is proportional to the displacement, but in the opposite direction. What's the answer if you want to solve? It's some sort of sinusoid that looks like this. One more step. Let me just move this over on this side. So same equation, I'll just rewrite it. I'll just move this on the same side. Right, because I just want to show that that's a second order ODE. Okay, I'll leave it like that, right? Here's our second order ODE. And what is the solution? What is X? Some sort of sinusoid that looks like this. This is the amplitude. This is the angular frequency. This is the phase angle. And then if we take a derivative of this, then you would get velocity, right? This is velocity. So let's take a derivative. Okay, and then let's take one more derivative, which would be acceleration. And if you take a look, this is the function x. So then minus omega squared, this is x. Right? And if I move this on the other side of the equation, then it looks like this. And then take a look. See here? See here? That means omega is square root of k over m. Right, so then we got this part of the solution. And then how do you get this and this? You would need to use the initial conditions, like in that last video. Okay, now let's compare this to a pendulum. Let's say there's a string of length L and then some mass over here. Okay, and let's say I pull the mass over here and then let it go, and then it swings kind of back and forth, right? It's oscillating. So let's try and solve for this angle as a function of time. So how do we do that? So the free body diagram just looks like there's tension in the string, there's weight, and then that's it. Let's see. So if the angle is increasing counterclockwise, so for example, if it's just like this, let's say we call that 0 degrees, then if it's like this, that's positive, like say 30 degrees, 45 degrees, 60 degrees. So if we're calling counterclockwise positive, why don't I pick a coordinate system that is, let's say if I go like this, if x is here, y is here, that means z is this way, counterclockwise out of the page, and I'll put the origin over here where the pendulum is pivoting. Okay, so if I sum torque about that pivot point, let's say the hinge of the pendulum, then what is the torque? So it's, well, let's look at this picture. From here to here, right, that's L, times, and then the weight is over here. Let's look at this picture. So the angle is here. So L times only the component of the force perpendicular this way. And so you see how that's opposite the angle? So that would be mg sine theta. And this torque would go this way in the clockwise direction, which is actually in the negative z. So this should be a minus sign right here. Okay, so this is the torque by the weight about that hinge. And then there's no torque from the tension, because see how it's that line of action is going right through that point. Equals I alpha, which I is this. Since we sum torque about the hinge, it's the moment of inertia about the hinge, which in this example is just, let's consider this to be a point mass. So the moment of inertia of that point mass is just ml squared. Okay, and then notice that angular acceleration is the second derivative of the angle, like this. So if I write all this together, so I alpha, ml squared alpha, and then why don't I move this on the other side of the equation, plus lmg sine theta equals 0. Okay, why don't I just divide everything by ml squared? Okay, so this is gone. And let's see, some things cancel over here, right? ml over L. Mass, oops. Okay, I'll just rewrite it. Okay, there we go. And let's make this a little bit simpler. Let's consider a pendulum where this is swinging for small angles. Okay, so for small angles. For small angles, sine theta, this right here, is about equal to theta. And what does small angles mean? Let me get my calculator over here. Okay, so see, let me put my calculator in radians. Okay, so you see here, I have my calculator in radians. So let's say you have 1 radian. And then what is the sine of 1 radian? 0.84. That is not very close. It's like 16% error. So let's pick a smaller angle. Let's say 0.5 radians. What is the sine of 0.5? 0.48. That's like 4% error. So let's go even smaller, half of that, 0.25. So what is sine of 0.25? 0.247. That's pretty good, right? That's about around 1% error. Okay, so let's see. So 0.25, that's like times 180 over pi. So that's like 14 degrees. Okay, so if you're like less than 14 degrees, that's about 1% error. Okay, so for small angles, we can make this approximation. So then sine theta is about theta. Okay, now take a look at what we have here. Look at these two. Right? It's the same form, which means, and you already know how to solve this, which means you know how to solve this. Right? It's the answer, theta, is some sort of sinusoid, cosine omega t plus phase angle phi. And then, right, let me fast forward to the answer we got over here, right? This angular frequency, this was root k over m, which is just the square root of whatever was sitting over here. So over here, the angular frequency is the square root of whatever is sitting over here, g over l. Right, and then how do you find the amplitude and the phase angle? You need to use initial conditions. Okay, and what is the frequency? So this is angular frequency in radians per second. What is frequency? 1 over 2 pi omega. So like this, that would be in hertz. What is the period? The reciprocal of the frequency. So just take the reciprocal of this. Okay, now for those of you in lab, when we did the pendulum lab experiment, I said that the period is a function of the length and g, like this, with no explanation. So here is the explanation. Right, so this is where it comes from. Okay, let's try one more example. How about instead of just a mass on a string, let's say you have some, like, here's your prototype wind turbine blade that is at some angle theta. Let's say theta is positive going clockwise. Okay, so let's solve for that as a function of time. And we would need to know some information about your turbine blade. So here's the free body diagram. So there would be weight acting at the center of mass, and then some normal force up here at the hinge. We're not sure the angle nor the magnitude. And we would need to know information about your pendulum. Right? We need to know the location of the center of mass. So we need to know this right here. I'll call this the distance to the center of mass. We need to know the moment of inertia about the center of mass. You can use the parallel axis theorem and get the moment of inertia about the hinge. Right, so if this is the hinge over here. Okay, so let's sum torque about the hinge. So let's say I'll pick coordinates. If I say this is x and this is y, that means z would be positive going clockwise because the angle is positive going clockwise. That's why I picked that. Okay, so there's torque from this force going this way, which is actually in the negative direction. D, center of mass, right here to here, times only this component of the weight, which is opposite the angle. So mg sine theta equals I alpha, which I is this. Since we sum torque about the hinge, this is the moment of inertia about the hinge. Okay, so then let me just rewrite this. I alpha is d squared theta by dt squared, the second derivative. And then I'll move this on the other side of the equation, so that becomes plus d center of mass mg sine theta. And then I'll divide everything by that moment of inertia. Okay, and then for small angles, sine theta is about theta. Okay, now look at this. compared to these. All right, so this is this was the mass on the spring. This is the pendulum that was just a string and then a point mass. All right, this is the mass in the spring. And this is our physical pendulum, just some object that has some moment of inertia, some center of mass. See, and what is the answer here? Theta would be some sort of sinusoid. And then this angular frequency would be the square root of whatever is sitting right there. Okay, so let's try a more specific example. Let's say it's just one slender bar. Then where's the location of the center of mass? Let's say it's a slender bar of length L. So the center of mass is just halfway, right? L over 2. Let me write this nicer. All right, the distance to the center of mass, I about the hinge. Okay, so the distance to the center of mass in this example, if it's just a slender bar, would be halfway, L over 2. The moment of inertia about the center of mass for a slender bar is 1/12 ml squared. The moment of inertia about the hinge would be 1/12 ml squared plus extra. How much extra? The mass of the bar times the distance between these two axes squared. What's the distance between these two? L over 2. All right, so that's 1/12, 1/4. 1/12 plus 1/4 is 1/3. Okay, so it would be L over 2, and then the moment of inertia about the hinge, 1/3 ml squared. That would be the answer. And then things would cancel here, right? Like m, mass would cancel over here, L over L squared, and then 1/2 over 1/3. Let me just flip those around, would be this way, right? So this would be the answer if it were just a single slender bar. Okay, so give these problems a try, and then let me know if you have questions. I'll see you in the next video.